Hey, I'm Ben Jones from the University of Washington. Today I'll be talking about Automate, a dataset and learning approach for automatic mating of CAD assemblies. This is work I did with Dalton Hildreth, Du-Wen Chen, Ilya Baran, Vova Kim, and Adriana Schultz. What do all of these objects have in common with each other, and most manufactured objects? They were all made using computer-aided design, or CAD, tools. These objects are complex and are not modeled as individual parts, but rather as assemblies of parts that interact with one another. The relative positions and degrees of freedoms of pairs of parts combine to make the complex motions you see here. In CAD, creating an assembly from parts is a time-consuming manual process of selecting, placing, and mating parts, which requires both careful position of the parts in reference to one another, as well as specification of how these parts can move relative to one another. In practice, users spend roughly 1/3 of their time in modern CAD tools in assembly work. In this work, we develop novel machine learning techniques for predicting how to mate parts. In our tool, the user selects the parts they want to mate, and our system suggests mate locations and articulation types. There's been a lot of work in machine learning for assembly modeling in recent years. While impressive results have been achieved in aligning parts to build assemblies, none of these works use CAD native data formats. They work with approximate geometric meshes or point clouds, rather than exact parametric CAD geometry, and learn rough positional alignment rather than exact constraints on parametric entities. There's been an explosion of interest in learning on CAD data in the last few years. In 2019 and 2020, 3 curated datasets of CAD models were released: the massive ABC dataset of BREP models, the Sketchgraphs dataset of constrained CAD sketches, and the Fusion 360 Gallery dataset of CAD models and their generative programs. Unfortunately, none of these datasets are suitable for solving the mating problem since they have no assembly data. Recently, several graph neural network approaches have emerged to learn features on CAD data, but again, these are insufficient for this problem since they simplify some of the topological complexity of BREPs necessary to mating. In this work, we make 2 primary contributions to address these issues. The first is the Automate dataset, a new collection of CAD assemblies that includes information about how parts are connected and their degrees of freedom. The second is a graph network architecture for CAD representation learning that can capture the full topological complexity. So I'm going to talk about 4 things today. First, I'll tell you about the structure of CAD geometry and mates, and the dataset we have collected for assemblies. Next, I'll discuss our new representation learning strategy for CAD data. Third, I'll tell you about an application for this representation learning, a recommender system for CAD mating, and finally, I'll discuss our experimental evaluation of the system. So let's talk about CAD data. The advantage of CAD data structures for mating is their exact parametric geometry that allows for precise constraints to be defined relative to it. How is this achieved? The parametric boundary representation splits a shape into 4 types of topological entities: faces, edges, vertices, and loops of edges. These entities have associated parametric geometric functions, for example, the equations of a plane, circle, line, or point. Topological relationships between these entities determine their final geometry. Loops bound and clip faces, edges make up loops, and vertices bound edges. These topological relations form a natural graph structure. Let's replace each entity with a node. Then we can draw an edge from each bounding entity. The parametric geometry information stored in the nodes and boundary information conveyed by edges fully define the shape. A mate in CAD is a constraint between 2 parts which defines how they can be positioned relative to one another. There is not a single standard for how to build these constraints, so in our system we define mates by a pair of mating coordinate frames, 1 on each part. In this hinge example, these frames are in the center of the hinge pin circles. When the parts are mated, these coordinate frames are constrained to be coincident. However, we also need to specify the functionality of this hinge, so we allow a z rotational degree of freedom. In our system, 8 types of motion are allowed, called mate type: fastened in place, revolute around the z-axis, sliding along the z-axis, planar translations in x and y, spherical ball joints, and common combinations of these rotational and translational degrees of freedom. So how do you define these frames? To ensure proper mechanical function, the mating coordinate frames need to be defined to the same precision as the parametric geometry. To achieve this, CAD mates are defined in reference to the topological entities. Let's see how this works in the context of the hinge pin. Zooming in on the pin, let's look at the BREP graph around this point. We want to place a mating coordinate frame at the center of the pin. To do this, we need 2 references. one to this inner circle to specify that the origin of the coordinate frame is at the center of the circle, and one to the planar face on top of the hinge pin, specifying the coordinate frame is oriented normal to the face. The unique format of CAD geometry mates requires a unique dataset to learn from, and no such dataset had previously been collected. To learn how to mate parts, we scraped and cleaned all of the publicly available assemblies in Onshape, a free-to-use browser-based CAD system. We will be releasing this dataset, which has nearly 100,000 unique assemblies, over 500,000 unique mates, and around 380,000 unique parts. Now that we've collected this data, we need a way to generate features for learning. Our goal is to learn embeddings for each topological entity in a BREP for use in downstream learning tasks, for which we have two main criteria. The first is to handle all four types of topology. Previous GCNs for BREPs have used a simplified BREP graph with just face nodes and edge links. This is insufficient for mating, since mating frames can reference any sort of topology, for example, the center of a negative space formed by a loop or a corner vertex. The second is to capture as wide of a receptive field as possible in order to understand local geometry. The first property means our graphs are heterogeneous, which is a problem because it makes GCNs memory intensive, and BREP graphs can be very large. And needing a wide receptive field to capture these large BREPs is problematic because this means a deep GCN, which is notoriously difficult to train past 3 or 4 layers. Our architecture addresses both of these problems. So how do we do it? The key insight is that BREPs are not arbitrary heterogeneous graphs. There is a distinct layered structure. If we gather the nodes by topology type and arrange them in 4 layers, vertices, edges, loops, and faces, we notice that edges only exist between adjacent layers. This will let us convert expensive heterogeneous message passing into a series of simpler homogeneous message passes. This layered structure is our starting point to construct a message passing network and gives our network its name, the Structured BREP GCN, or SBGCN. As our input, we take the structured graph with node features of the parametric functions and their arguments, along with computed geometric properties like surface area, length, and center of mass. These input features are embedded into a common dimensional space before convolution begins. First, we pass messages from vertices to edges. For this, we use a max relative GCN with residual connections that Lee et al. Found to help GCNs deeper than 3 or 4 layers converge. We continue this from edges to loops, and then from loops to faces. If we were to immediately pass back down the structure, then back up again to expand the receptive field, we would need a very deep network and an appreciable receptive field. This is because the shortest path between adjacent faces is length 4. To mitigate this, we introduce metapaths, a shortcut edge that jumps directly between adjacent faces. Doing this effectively reduces the diameter of our graph by 3/4, allowing us to get a wide receptive field with far fewer message passing layers. With these meta edges added to our structured graph, we pass messages from face to face for n layers. This parameter controls the receptive field size, and then finish by message passing back down the structure from faces to vertices. This efficiently produces embedding vectors for each type of topological entity that captures information from a wide receptive field, satisfying all our requirements for representation learning on BREP topologies. So we have a way to learn BREP topology embeddings. What can we do with it? We use these embeddings to build a recommender system for mates. Our recommender system is designed to fit within existing CAD assembly workflows. While creating an assembly, whenever a user selects faces on 2 parts, our system first uses these selections to generate a collection of potential mates. Then it uses SBGCN to score and rank these mates, the top 6 of which are presented to the user to choose between. The first step of the system is generation of potential mates. Recall that a mate is a relationship between 2 mating coordinate frames, each of which is defined in reference to 2 topological entities. So a potential mate needs 4 topological references. When the user selects faces on 2 parts, we use these selections both to choose the parts to be mated, as well as the orientation references. For potential mates, we also need coordinate frame origins. We assume these will be near the user's selection, and so find all locations that are topologically adjacent to the selected face. We create potential mates using all pairwise combinations. This can result in very many potential mates. We need to reduce these suggestions before passing them to the user. We treat this as a ranking problem and use a Siamese network configuration of our SBGCN to create features for each potential mate. A simple fully connected network then scores each. These are ranked and the top 6 are presented to the user. If the user selects one, another fully connected network is used to classify the mate type. Let's look at how we evaluated the system. We split our evaluations into two different tasks, since we make two different types of predictions in our system. Mate location, which predicts the mating coordinate frames given two parts and faces, and mate type, predicting the type of articulation given a ground truth mate location. We will first look at some quantitative metrics, then subjective evaluation of expert CAD users. Let's start with mate location. What do our predictions look like? Here, the user has selected a bracket face and the end of a complicated aluminum extrusion. From these two selections, our system generates over 7,500 potential mates. Here are the top 6 in its ranking. For the most part, it wants to align circular bolt holes on each part. In our dataset, these two parts are actually mated like our fourth prediction. This ranking position of the mates in our dataset is our primary evaluation metric. Aggregated across all of the mates in our test set, this is hit ratio at k predictions, the percentage of examples that we predict the correct mate within the first k options, plotted here. Our system gets the correct mate first just over 40% of the time. Since we show 6 selections to the user, the accuracy of our UI is the hit ratio at 6, or 72.2%. For context, a random ranking of potential mates would work only 30% of the time. As a baseline, we also compared against a common technique from the assembly modeling literature, representing the parts as point clouds and regressing the relative positions of the two parts. We used 3 popular point cloud networks, PointNet, PointNet++, and Dynamic Graph CNN. All 3 performed similarly and did not approach the accuracy of our model. Why is this? Let's look at how the baseline predictions are made. First, we pre-aligned the parts to the centers of the selected faces, so we only need to predict offsets from these centers. We then snapped to the nearest potential mating frame as generated by our system. For ranking, we sorted by distance from the offsets. The top bracket here gives a hint as to what is happening. There are many frame locations clustered near to our predicted offset, so even small errors can generate an incorrect selection. To quantify this, we tried ground truth offsets with increasing amounts of noise. Here we plot a ranking metric against noise magnitude. With perfect predictions, the system performs optimally, but very quickly drops off with just small amounts of noise. This experiment highlights the need to use CAD data formats for CAD mating. Other structures do not offer the necessary precision to make the exact predictions needed in mechanical modeling. Now let's look at the mate type task. These predictions are made assuming the correct mate location is already chosen. Our system gets the correct mate type just over 70% of the time. For reference, a baseline of ranking mate types by their frequency in the dataset is roughly 62% top 1 accurate. We also ran the same 3 point cloud baselines. Our system still outperforms these, but not by as much as in the location task. However, our model is far more efficient than the point cloud models. It has only 126,000 parameters, whereas the point cloud models have between 834,000 and 1.5 million parameters. It also turns out that our model is about on par with human performance. This is because mating is ambiguous. Suppose you are choosing a mate type for these bricks. If they are in a wall, you may consider them to be fastened in place. Or you may wish to model that they can slide apart, or additionally rotations around the connecting peg. To quantify this ambiguity, we asked 7 CAD experts to manually label parts of our test set and measured the pairwise agreement between the experts using Cohen's kappa. This is a 0-1 scale, and the median pair of experts has just a 0.4 agreement, meaning there's a high level of disagreement. We also measured the agreement between experts and our dataset labels, which had even lower agreement. But interestingly, the median human expert is exactly on par with our model's predictions in agreement with the dataset labels, indicating that our model is doing about as well as humans can on this task. There's also ambiguity in mate location. Consider the location example we looked at earlier. Our model predicted the label position 4th, but all of the top 4 selections look reasonable, aligning the bolt holes between parts. We also asked a CAD expert to label which of our predictions were reasonable. That is there a context in which that suggestion would be useful? These are indicated by green check marks. All of our top predictions were good predictions, just not the use case that we have labeled in our dataset. This is a fairly common pattern, like this case, or this one. So the accuracy numbers we showed earlier are best thought of as a lower bound. This ambiguity motivates future work for us. Zooming on that last example in its context, we see that the choice of holes to align with was dictated by the context of a motor mounting. which we did not tell our system about. We would like to incorporate more parts into an assembly context when predicting mates to better capture design intent. Complementary to adding assembly context, we'd like to further explore interaction techniques to capture design intent in ambiguous situations. Finally, we would like to incorporate more intrinsic geometric features. Concurrently developed BREP graph networks do a good job of this, and generally follow the same convolutional patterns as the metapath portion of SBGCN, and so are good candidates to incorporate within the SBGCN architecture. Thank you so much for watching. We are excited to see what you do with the Automate dataset and the SBGCN architecture.